Hello everyone, I'm Pengfei Li from Zhejiang University. I'm very happy to share this work with you. The work is entitled HisRect Features from HisRect Visits and a Recent Tweet for Co-location Judgment. It's a joint work with Hua, Qian, Shijian, and Gang. Okay, let's begin with the motivation. In this work, we study a co-location judgment problem, that is to judge if two data users are at the same point of interest in a period of time. Knowing if two users stay together enables a wide variety of social network applications, such as friend notifications, community detection, and local people recommendation. The problem of co-location judgment on tweet data is challenging. On the one hand, the content length of each tweet is limited to 140 characters, and thus a tweet conveys little information. As Twitter users often use non-standard and shorthand terms, tweets are often vague and noisy. Thus, it's difficult to find location clues from short, noisy tweets. On the other hand, as tweets are mostly not geotagged, and even fewer tweets are associated to POIs, the labeled data across each POI is scarce. We propose two approaches to address the challenges. First, our solution integrates user visit history and recent tweets in feature selection. A user's historical visits can be regarded as a kind of prior information, whereas his recent tweet is often related to where he is or hiding true. To alleviate the issue of data scarcity, we further propose a semi-supervised learning framework that leverages unlabeled data to train our feature generation function. I will introduce the solution in detail soon. Before formulating our co-location judgment problem, let me introduce some definitions and notations. Let P contains all POIs. A tweet is geotagged if it is sent with coordinates. A geotagged tweet T is a POI tweet if it has a POI P such that T's location is covered in P's extent. A visit is a three-tuple TS latitude and longitude. In the training phase, we extract visits from all geotagged tweets in a user timeline, which forms a complete sequence of visits of the user. Such a sequence is called the user visit history. Furthermore, we built user profiles that combine user visit history and recent tweets. A user profile R is a four-tuple UID TVV history PID, where UID identifies the user who sent the recent tweet. vHistory is the user's visit history before t.ts, and PID is a POI identifier. If I.t is a POI tweet, R is regarded as labeled. Otherwise, R.PID is set to null and R is unlabeled. In the co-location judgment, we consider a pair of users. A pair is a three-tuple pair Rj equal to Ri, Rj, and co-label, where R and Rj are two profiles with their UIDs are not equal, and the difference of their time steps is less than delta t. A pair is unlabeled and its co-label is set to null if either of each profiles is unlabeled. Otherwise, the pair is labeled. In a labeled pair, co-label is set to 1 in the training data. If the two users are co-located at the same POI, such a pair is positive. Otherwise, co-label is set to 0 and the pair is negative. We use gamma L minus, gamma L plus, and gamma U to denote the sets of negative, positive, and unlabeled pairs, respectively. Specifically, the labeled pairs set gamma L equal to the union of gamma L minus and gamma L plus. With the above definitions and notations, we can formulate our research problem of co-location judgment. Given two profiles Ri and Rj generated by two new users, such that Ri and Rj form a pair, suppose that the two profiles' PIDs are unknown. Decide if they are co-located, in other words, if they are from the same POI. Next, we will introduce our proposed framework for solving the problem of co-location judgment. This page shows the framework of our solution to the co-location judgment problem. The goal is to extract features from historical visits and recent tweets in profiles. The left part illustrates how it works. The HisRect feature of the profile R includes two parts. The first part is a fixed dimensional feature FVR, which quantifies the spatial and temporal aspects of historical visits. FCR is the second part. It extracts the location clues from the raw recent tweet contents using skip-gram algorithm and bi-LSTM-C, a variant of bidirectional LSTM. Also, it's a fixed dimensional. To train this featurizer, we propose a graph-based semi-supervised learning approach, as shown in the right upper part. The SSL framework takes pairs and labeled profiles as input. It needs a similarity matrix A that measures the distance of both profiles in a pair. After that, each profile is expressed as a fixed dimensional feature vector. Finally, the right lower part shows the procedure of judging if a pair Rj is co-located or not. Using F, we calculate the difference of features of Fri and Frj and feed it into a binary classifier. It's noteworthy that the parameters of F are fixed during this stage. The HisRect featured FR of a profile R includes two parts. FVR features R.vHistory. FCR is the embedding of R.content. To obtain the final HisRect feature of FR, we merge FVR and FCR through vector concatenation and feed it into a feed-forward neural network. In a short period of time, a user is unlikely to move from one POI to another that is far away. Therefore, a user's historical visits have an impact on his current locations. Intuitively, more recent tweets tend to have a higher impact. It's thus beneficial to utilize a user's visit history by considering both temporal and spatial aspects. More specifically, we want to know where the users have been before, when they went to those places, how far the places are with subsequent POI candidates. To quantify these aspects, we propose a featurizing method that considers all of these aspects. It's shown in the upper part of this page. Above dvPI is the spatial distance between the visit V and the ith POI PI. The ith item in WV is the spatial relevance matter between V and PI. The coefficient yt divided yt plus r.ts minus v.ts is an influential factor of the time step of V. Parameters yD and yt are distance concerned and time concerned smoothing vectors respectively. It is evident from the definition of FVI that if the user has ever been to some places close to some POI PI, the ith weight in FVI will be large. To get FCR of a profile R, R.content is first converted into a word vector sequence X using the skip-gram algorithm. Then X is fed into bi-LSTM-C, which adds a convolution layer above the bi-LSTM layer and is able to extract the local features inside the word groups. The fixed dimensional output of the bi-LSTM-C is just the FCR. It's natural to train F by feeding HisRect features to a POI inference classifier. However, a supervised method falls short when there lacks sufficient training data. In our case, the amount of unlabeled data is almost 3 times larger than that of labeled data, according to our statistics. This motivates us to employ a graph-based semi-supervised learning method to leverage unlabeled data to generate better features. Our SSL approach aims to solve the optimization problem, shown in the upper part of this page. N is a normalized vector function space, and LPOI is a supervised loss. E is a normalized feed-forward network to embed the HisRect features of profiles. The unsupervised loss LU takes the labeled and unlabeled pairs set as input, and AIJ is the similarity between profiles RI and IJ. Two profiles should be similar if they are associated to the same POI in the same time period. In contrast, the two profiles in a negative pair are supposedly different, as they are associated to different POIs. Accordingly, a penalty should be given if the distance is large between features of profiles in a positive pair. Otherwise, it gives a negative penalty. Therefore, we set the similarity item AIG for profiles in positive and negative pairs to be 1 and -1 respectively. When a pair of profiles are not from the labeled set gamma L, we cannot measure the similarity in the aforementioned way. For profile pairs from gamma L, we utilize their spatial and temporal information. Intuitively, the shorter the spatial distance between two profiles, the larger the similarity between them is. Given a profile pair, if their spatial distance is larger than rho or their temporal distance is larger than delta t, we set the similarity to be 0. Furthermore, if a profile R was posted in a place close to no POI, we think it offers little useful information and set all the similarities involving R to be 0. Those relevant profiles are unlabeled and we are less confident to say their features are totally different. Therefore, we don't set them to be -1. After getting the HisRect feature as f, judging if two profiles I and Rj are co-located is simple. We use an embedding layer E' to embed the HisRect features of I and Rj. Also, we construct a feed-forward neural network C whose input is a difference vector between the two embeddings. On top of C, follow the binary softmax layer. We train E' and C using routine neural network gradient descent methods, but note that the parameters of f are fixed at this stage. Finally, let me show you some experimental results. We crawl timelines of two users whose profile location is in one of New York or Las Vegas. In the data we use, most POIs involve no tweets. Therefore, we only consider the top 1,000 POIs in NYC and the top 250 POIs in LV that have the most tweets. We filter out the user timelines that contain no POI tweets and obtain about 59,000 and 11,000 user timelines in NYC and LV respectively. We compare the performance of our proposed approach with 10 alternatives. Specifically, TGTIC and Ngram GAUSS are two existing approaches. HisRect SL is the same with HisRect, but it uses the supervised training. And the other approaches use different techniques to extract features from profiles. It is also evident from the table and the figure that our HisRect performs best. HisRect performs better than other alternatives on all of the evaluation metrics. Its AUC values are also the highest in both datasets. In order to better understand why HisRect features work well, we conduct an interesting experiment. We get the HisRect features FR for every profile R in the top 5 POIs in the testing dataset, and use TSNE transformation to visualize HisRect features. It can be seen from this page that only a small central part mixes different POIs and results in queues. According to our observation, the contents in the profiles displayed in the center can hardly find local clues. Except for the slight queues, most profiles that come from the same POIs are adjacent to each other and form clusters. We also investigated the performance of HisRect features on the POI inference problem. It is clear that our HisRect performs the best. It is the only one that achieves accuracy higher than 64% and 70% on NYC and LV datasets respectively. My presentation is over. Thanks for your watching. Hope everybody is healthy. Thanks.